Hi. In this problem, we're throwing a dart at a circle. And the circle has radius of r. And what we assume is that we always hit the target. So whatever we throw, the dart always lands somewhere within the circle. Right? So we don't miss completely and hit out here. And the other thing we assume is that any point, all points within the circle are equally likely. All right. So that's the setup of the problem. And what we're asked to do is to come up with some distributions, some densities. And the first thing that we'll do is we'll define two random variables. Right. So we'll define random variable x to be the x coordinate of the of where we hit on the target, and random variable y to be the y coordinate. So now we have these two random variables, and the first part of the problem is to calculate what the joint PDF is. So what is the joint PDF of x and y? Well, in this case, it's not so bad because we are told to assume that all points are equally likely. So what does that mean? That means that within the circle, which is where the target is, it's uniformly distributed. So all points are equally likely. So all we have to do now to find what this joint PDF is to calculate what this area is and take 1 over the area. So it's 1 over the area, and as you know, the area of the circle is pi r squared. So it's just 1 over pi r squared when you're within the circle. And what is the equation of a circle? The equation of a circle is x squared plus y squared equals r squared. So we're centering the coordinate system at 0, 0. That's where the circle is centered. So we lie within this circle when x squared plus y squared is less than or equal to r squared. And we always hit the target, so we never fall outside of this circle. Right? So within the circle, it's uniformly distributed, and the normalization or the scaling factor is 1 over the area, and outside it's 0. All right. Then the second part asks us to find the conditional distribution of x given y. So what is the distribution of x given y? Well, the distribution of x given y, we know we can calculate that from taking the joint PDF of x and y and dividing by the marginal of y. Okay, so first let's calculate what the marginal of y is. The marginal of y, when you calculate a marginal, remember, it's just a matter of taking the joint and integrating out the variable that you don't want anymore. So in this case, we're integrating out x. And in general, you integrate from x equals minus infinity to infinity. Right? But in this case, we need to be careful what the limits are and only integrate when the limits are valid. So for now, let's just write minus infinity to infinity, and we'll fill that in. So we know that the joint PDF is just 1 over the area, 1 over pi r squared. Now, when is this joint PDF actually valid? Right. So now let's fix some value of y that we want. Let's say it's this one right here. This is the value of y. Well, given that that's the value of y, what range of x is this joint PDF valid? Well, it's valid for the range of x that falls within this band here, from here to here. Now, what are these two values? Well, if y is here and the radius is r, and we know that the equation of the circle is x squared plus y squared equals r squared, then we know that this point has to be x has to equal square root of r squared minus y squared. That's the value of x that corresponds with that value of y. And then similarly, here we have minus square root of r squared minus y squared. So that's the range of x's for that value of y. So that actually becomes the limits of our integration. And the good thing is that this is just a constant, right? There's no y in here, and so we can just pull that out, and really it just becomes an integral of a constant from or integral of 1 from minus square root of r squared minus y squared to square root of r squared minus y squared. So it actually is just going to be 2 square root of r squared minus y squared over pi r squared. And again, this is valid only for y from minus r to r, and it's 0 otherwise. So why is that? It's because, well, no matter what, y can only go as high as the radius in either direction. So y is bounded between minus r and r. And so another way to look at this graphically is you're just taking this joint PDF and squishing it to the y-axis. Right? And so the only parts that will get non-zero contributions are the ones from r to minus r. And note that although the original joint distribution was uniform, we assume so, when you take the marginal of y, the marginal of y is not uniform. Right? Notice that it actually depends on y here, and it varies depending on what y is. And it turns out that it will be largest when y is 0 and smallest when y is r or minus r. Why is that? Because when you squish this, you get more contribution when you're at y equals 0. Right? It's more likely for y to be 0 because there are a lot more corresponding x's that pair with that y equals 0. And when you're all the way up here, there are very few other x's that will pair with that. Okay, so we found the marginal distribution of y, and now all that's left to do is to calculate out what this quotient is. So we have the joint distribution and we have the marginal, so let's just calculate out what the conditional distribution is. Okay, so the numerator is just 1 over the area. And the denominator is this. 2 times square root of r squared minus y squared over pi r squared. And of course, we can do some cancellations and simplifications. But the first thing we want to do is, as always, to check what range this is valid for. So the numerator is the joint distribution, and that's valid for any x and y pairs that fall within the circle. And the bottom is valid for any y that is between minus r and r. And so what this tells us is that this is in fact valid for any pairs of x and y that fall within this circle. So it's valid for x squared plus y squared less than or equal to r squared. And outside of it, it's 0. And what we can do is simplify this a little bit, right? Because this will cancel out with the top. And what we're left with is just 1 over 2 times the square root of r squared minus y squared. And note here now that for any given conditioning on y being some value little y, this conditional density of x no longer depends on x. So it is in fact uniform along a certain range. So another way to write this, another way to write this range is maybe a little bit more explicit, is that y has to be between negative r and r, right? So that's what you're conditioning on. You know that y can only be these values. And then given that y is that little y, then this is true for some range of x. So given that y is some value, you know that x can only go from minus y squared to positive square root of y squared minus y squared. Minus square root of r squared minus y squared less than x less than or equal to square root of r squared minus y squared. So it's doing the analogous calculation as we did earlier. And so what we see is that it is in fact uniform, right? Because it doesn't depend on x. And why is that? It's because when you take conditioning on y being some little value, it's, as we talk about, it's as if you're taking a slice along that value. And now remember that the original joint distribution was uniform. So it was like a round cake that was flat. And now you take a slice of that cake, a horizontal slice, at some particular value of y. Well, when you take that slice, then you know that if you can imagine it, coming out of the board, this distribution of x will also be still flat. So the distribution of x will still be uniform. And that's what you get here. So it's interesting that the original distribution is uniform, but when you marginalize it and take the marginal distribution of y, you get something that is not uniform, or it depends on y. And by symmetry, you can say that when you marginalize out y and take the marginal distribution of just x, you will also see that the marginal distribution of x is also not uniform. But when you then calculate the conditional distribution, you get a uniform distribution back again. And that's because you're taking this slice, right? The reason is that depending on where the slice is, you get a longer slice. And that because of that, the marginal distribution becomes higher at closer to the axes and smaller when you go to the extremes. But as long as you know that, and you condition on just taking some slice, within that slice, the distribution will be uniform. Okay, so this is just a slightly different kind of joint distribution with a circular shape. Right? Mostly we've been dealing more with kind of angular distributions. And so you can see that even with circular distributions, you get something, you can still apply the same kind of methodologies and tools to get the answers that you want. All right, so I hope that was helpful, and see you next time.